Okay, today we're going to talk about clouds and precipitation and how we detect and look at them. Uh, we talked about moisture, so you've got all that. In reality, we're interested more in why did the clouds. Uh, so I thought I'd just start looking at clouds. We're looking at a visible satellite picture here. It was infrared and switches to visible as the sun is moving across the sky here. I wanted you to notice the snowpack. Look across Illinois, Indiana, even into Ohio, and you'll see a band of snow that stretches pretty nicely right straight across it. You can see the Chicago area, for example, there's no snow, but the midsection of Illinois has it, and you can even see the rivers in it and all that. This is a tool that is so useful with satellite. You can see where the snow has fallen, but you can also see where the clouds are. You actually can detect the motion of the clouds here, how they're coming off the lakes. You can see in the middle of Lake Michigan, for example, clouds are beginning to form and moving across. One of the questions you've had, in many ways, was what happened to an air parcel as it moved across Lake Superior? Well, guess what? You're seeing it played out right there. What happened to that air parcel is it got warmer, it became more unstable, and it got more moist. And with that, it began to produce clouds as it moved across Lake Michigan. You can see bigger, bumpier clouds coming across Lake Erie and all as well. And what's really weird, not happening in a lot, but there's bands of clouds, what appear to be clouds on the east side of the mountains in Appalachians, in Maryland there and all, and up into Pennsylvania. Actually, that's snow on the ground. The higher, because it was so close to freezing, the higher the elevations were, the more snow fell, the brighter it became. The lower the elevations, the less snow fell, and the more it melted. As the day wears on today, you'll actually see as temperature goes above freezing there. And you can see in West Virginia, the mountains, the orographic effect, the lift from the mountains, keeping clouds on the west side of the mountains. And Southeast Virginia doesn't even have any clouds. Interestingly, as part of this chapter, we're going to talk about radar. And you saw some bigger bands coming across Lake Erie that I pointed out, and there's one that actually is occurring and moving in through Cleveland right now, and coming into the southeastern part of Lake Erie as well. They're coming off of other lakes. So you can actually see lake effect snow. Radar is a great tool. It picks out these air precipitation. What it does, it sends out a microwave pulse and then listens. It actually listens 90% of the time, and only 10% of the time is it sending out the pulse. The idea is to hear the echo return from whatever it's pinged off of. And the stronger the return, the more likely it is heavier precipitation, bigger raindrops, bigger snowflakes, more snowflakes, hail, big raindrop there. All of that would be a bigger return coming in, which would indicate heavier precipitation. So you can see the darker greens around Cleveland would indicate heavier snowfall. The lighter ones up across some other areas down to the south, across Akron or Mansfield, much lighter snowfall. So that is what you're looking at when you see a reflectivity return. If you looked at a return for Doppler return, which would be, think about it, when you hear a train go by or a car pass you, it changes frequency. It sounds different. It's exactly what happens with these pulses of energy sent out. They change frequency, and when they do, we can detect that, and we can calculate from that motion of the little particles. So we're picking up air motions of all the precipitation. Anything that's reflected to the radar, we can determine a motion of. And guess what? Bugs actually reflect. If you have a look at a strong front. Your winds are converging into that front. We've talked about that. And there'll be bugs, literally, that accumulate along a cold front or a warm front. And we can actually pick out cold fronts and warm fronts sometimes by just looking at where the insects are. Now you've got the motions. An interesting thing happened a few years ago. We went to dual pole. What does that mean? Well, dual pole means we've always, before that, sent out just a horizontal pulse of energy. Now we're sending a horizontal and a vertical pulse of energy. So I can get a two-dimensional picture. What that means is I'm seeing the shape in 2 dimensions of a raindrop or a snowflake. So all of a sudden I can differentiate sizes. With that, I get better accuracy on how much precipitation is falling. And I can also determine where things change from snow to rain. So maybe I can see where the melting point is. I can also maybe detect, what a hail would look like. And was very useful in very bad, severe weather. If debris gets pushed up into the air from a tornado, which it does when it's a strong enough tornado, I can literally determine that it's debris and not rain. And if I can determine that, then I can tell you there's a tornado on the ground. Instead of having to wait for somebody to call me or whatever, I am able to detect that all with dual pole radar. So now with this, let's go take a look at some reflect. There we go. All right. So I wanted to show you this week and go through the slides a little bit quickly here. So we're talking about clouds and precipitation. Well, you would think, everything would be nice and easy. We have a cloud. Not so simple. Guess what? Literally, to have a cloud form, you must have cloud condensation nuclei. These can be things like salt put in the air by oceans, forest fires, dust from the ground. Why is that? Well, take a look at a raindrop versus a cloud drop. Notice how much bigger the raindrop is. So that cloud drop is very, very tiny. It means it has a sharp curve to it, a very sharp curve to it. Everything we have done pretty much flat. Here we have these raindrops that aren't flat. They're curved. And that droplet curves, and the smaller the droplet is, the more curved it is, the better chance that water is going to go back into a gaseous to 400% relative humidity to get a cloud droplet to form. Here is where that cloud condensation nuclei come in. They mix in and literally they dissolve in that little tiny bit of water that's there and allow it to hold on to its shape. They keep it from evaporating so that it can grow and gradually become a bigger raindrop. And here you see the example of all that. So with that, we have the salute effect, which is what I did, and how it requires supersaturation, except that it doesn't because of these dust. So every raindrop and every droplet in a cloud has a little bit of dirt in it, we'll say. Now, interestingly, as part of all this as well, guess what? These little tiny cloud droplets don't freeze. They don't freeze at 32 degrees. Why is that? Well, again, they're so small that the kinetic energy within them keeps them from freezing. So they need ice condensation nuclei. So they need another little thing injected into them that allows them to freeze. And generally this occurs at around -9 degrees Celsius or 16 degrees Fahrenheit. So a lot of times we have moisture in the cloud, water in the cloud that's well below freezing. So it's super cool. But once these cloud condensation nuclei begin to occur, we begin to get more and more ice forming with them as it gets colder. So they gradually change over to all ice. Precipitation also, when it falls to Earth, think about it. You have the resistance of the air. We've talked about the air having a resistance. It has pressure, and the more denser it is, the more resistance it has. So actually, precipitation has terminal velocities, meaning, there's gravity pulling it down, and the bigger the snowflake is, the more it's getting pulled down to the ground. It won't stay up in the air. So that is why it moves to the ground, because of gravity pulling it down. So how do these precipitation occur? We talked about clouds, and you see clouds a lot more than you get precipitation. There's actually two processes. One is a warm cloud process, collision coalescence. Guess what? Clouds aren't generally very warm. They're up in that colder air. So there's another process called Bergeron-Findeisen process. So let's talk about the warm cloud one a little bit first. If the air is above freezing, or maybe it's just slightly below freezing, and everything you have in that cloud is a raindrop. Think about in the tropics. You get one raindrop and it actually hits another little cloud droplet, we'll say, and hits another little cloud droplet. Well, eventually it gets big enough, it begins to fall. And if there's a bunch of cloud droplets in the way, it gets big enough and it keeps growing till it eventually comes a big raindrop down on the ground. This happens in the tropics, and it happens when there's a tremendous amount of moisture. It's the most efficient process for bringing all that moisture in the cloud down to the ground. Now, with the Bergeron-Findeisen effect, on the other hand, we have to have ice, or at least beginnings of ice. Why is that? Well, we've talked about vapor pressure of things, and guess what? If you have water, it has a certain kinetic energy moving in it. If you have a frozen substance, ice, it has a lower kinetic energy. So it's easier for water to accumulate on ice. The saturation pressure is lower over ice than it is over water. So therefore, the vapor pressure will be a gradient towards ice crystals. So when ice crystals begin to form in the cloud, the water droplets begin to move to those ice crystals, causing them to grow. As they grow, they get heavier and begin to fall out of the clouds as snow, and eventually melting into rain. So that is where most of our precipitation comes from. Almost all precipitation at our latitude begins as snow and then melts into rain towards the ground mostly. Sometimes it melts, it evaporates as it's coming down in virga. And there are different types of precipitation. We have rain. We have drizzle. Drizzle is very low, develops very low in the atmosphere, and is very tiny. We have snowflakes, and guess what? They don't all have the same shape. I wanted you to look at this chart. If I'm forecasting 6 inches of snow at your house, and it turns out that I get sector plates for the snow, still a snowflake, just much smaller than a dendrite snowflake, that 6 inches might become 3 or 4. So what we have learned is that We have to literally figure out what kind of snowflake it is to make a good forecast on what amount of snow is going to fall. If you have dendrite snowflakes, there's a better chance you're going to have heavier snow. We can look at where the most vertical motion is, where the most moisture is, and estimate what type of snowflake may be. But if we're wrong, we may get less precipitation. That's one way, or maybe there's other factors implying less precipitation. So forecasting the amount of snowfall is a rather complicated little process. And finally, forecasting what type of precipitation hits the ground. Think about it. Many, many times you wind up saying, oh, it's going to be all snow. What happens is if we know the cold front came through, we're on the cold side, but we also know that there's 3 dimensions to the atmosphere. So maybe that little bit of warm nose or the warm air from warm front has made it into our area. Aloft, maybe the temperature there is 34 degrees. Oh, that snow's melting now, becoming rain in that area. But it goes below that area, it's back into colder. Maybe it freezes to sleet. Maybe it's just a very tiny little bit below freezing. And remember, we probably have super cooled water hits the ground. That area that's frozen or just a little bit below freezing now becomes freezing rain. So you can see you've got to know the 3-dimensional structure of temperatures in the atmosphere in order to determine the precipitation type. That's why it's a whole lot easier in summer. I know it's going to rain. I know it's going to be never cold enough at the surface and all the way through the atmosphere to keep it as all snow. We showed you some radar. I just wanted to review it again quickly here, the reflectivity mode, the velocity mode. And yes, there's one of the radomes. They're pretty good size. You'll see them. I had one outside my office when I was working at Wakefield, and there was one in Sterling, Virginia. There's one in Cleveland, Ohio. There's another one in Wilmington, Ohio. There's one in Charleston, West Virginia. So they're around. There's 122 of them actually out there. And the Doppler effect again shows the precip motion. Interestingly, when you're in a thunderstorm, you can get circulations that really get to see the motion. Here, you have literally what looks like a hook, called a hook echo. And as part of that, you have 2 very strong wind motions moving very close to each other in opposite directions. This is moving counterclockwise, so it's a low pressure. That's literally a tornado that's beginning to form. Because the radar is picking up in the clouds, it's not looking at the surface, right down on the ground, it can't. So you're seeing this form up in the clouds. The idea is to predict that this is going to get all the way down to the ground. Many, many thunderstorms may have this rotation in them. Not many of them produce tornadoes. And the whole object is to determine if this is going to occur and bring it down to the ground. In this case, yes, it was occurring. And a matter of fact, we got to see the Doppler, the debris with this radar as well. Hurricanes, we can see the wind flow with them. Phased array would be a wonderful radar. We're never going to see it in my lifetime. It's on some ships out there, but it's a continuous radar. I got to play with it at Norman, Oklahoma once, and as part of that playing, I got to see it predicting literally see a tornado form, because you're seeing the whole column of air instantly. The phased array sends out a large, complete suite of radar waves, literally from the ground up over 50,000 feet, all at once. Whereas a Doppler radar that we use, the scan goes out maybe at 1.5 degrees, then it goes to 1.5 degrees, then it goes to 2. So we're always looking upwards, slowly but surely, and then we're coming back down and starting over again. Phased arrays all at once, so it's a really neat tool. However, they cost a few $1 billion, so we're never going to see them in the near future, at least around where we are. So that's what I wanted to get through today. We're going to, your discussion this week's about clouds. Take a look, see what you have going on in clouds. So let me know if you have any questions.